Welcome to qnawire.
For part A of this problem, we're asked to graph the velocity with respect to time. And so if I create a big plot here, my x-axis is time, and my y-axis is velocity. Looking at the range of the data they give us, it makes sense to make this far point here 60 and the time axis, and then up here I'm going to make it 260, just as good limits of our data. We're told that time is equal to 0, the velocity is 0, so this is definitely a data point. At 2.1 seconds, which is roughly a very small distance, like let's say here, the velocity is 60, which is somewhere around here. So that's a data point. So that's 60, that's 2.1. We're also given that at 20, which is about a third the way to 60, so roughly here, that's 20. The velocity is 200, which is close to, say, this point. And then we're also told that at 53, which is somewhere around here, 53 seconds, the velocity is 253, which is just a little less than 260. So about here. And so now we just have to connect the dots, and we expect that they connect smoothly. We don't expect the car to lurch once it is driving for 2.1 seconds or anything like that. So it's going to be a smooth curve, something like that. And so since the acceleration is the slope of the velocity curve, we see that the slope is changing. So the acceleration, not constant. It's constantly changing throughout this. And that's the end of part A. Part B asks for the average acceleration along the 3 time segments of the previous part. And before we do this, it helps to convert our given velocity values into meters per second because they're given in miles per hour. And so we have to convert 60 miles per hour into meters per second. And we do that doing a unit conversion. So we're going to have miles in the bottom and meters in the top so that we can cancel the miles. And in 1 mile, there's roughly 1,609 meters. We also need to convert the hours into seconds. So we're going to have hours in the numerators and seconds in the denominator. 1 hour is 3,600 seconds. The hours cancel, and we're left with meters per second. Plugging this into your calculator, you'll get 26.8 meters per second. Also, we need to convert the other speeds. So we also have 200 miles per hour. And just doing the same conversion, multiplying by 1609 and dividing by 3600, I get that this is 89.4 meters per second. And then lastly, 253 miles per hour is 113.1 meters per second. And so we'll keep these here for reference as we do the actual part here. So the average acceleration from 0 to 2.1 seconds is defined to be the velocity at 2.1 seconds minus the velocity at 0 seconds over the time between that, which is just 2.1 seconds. We calculated these in meters per second on the previous page. So v of 2.1 is 26.8, and v of 0 is just 0. And so when you plug this in, you get 26.8 minus 0 over 2.1, or 12.76. This is in meters per second squared now. Now the next part is for the next time interval. So the average acceleration here, I'm going to label this by 1 so that we can label this by 2, is velocity at 20 seconds minus velocity at 2.1 seconds over the difference in time of that, which is 20 minus 2.1. This is equal to 89.4 minus 26.8. I got these values from the previous page, over 17.9, which is the difference here. This is equal to 3.5 meters per second squared. And then lastly, the average acceleration of the last bit is velocity at 53 seconds minus velocity of 20 seconds over 53 minus 20, which is also known as 33. And so plugging in the values here similar to the previous steps, I get 0.718 meters per second squared. The last thing we're asked is if these values make sense given our graph on the first page. And you'll see that these values decrease. So it starts off with a really high average acceleration. It quickly decreases to 3.5, and then it decreases even further. And this makes sense with our graph here because the average acceleration is just resembled by the slope. And so we see the slope starts really high and then it decreases over time. And so yes, it does agree with the graph.